Okay, so let's do this question, and I'm just gonna jump straight to the test case. I think that's a helpful way to understand the question, and then I normally read it afterwards. But basically, this is a restricted edges problem, and basically you're given two nodes, S and T, inside a graph, and you want to see if there's any path between S and T where we use at most K edges, right? So looking at this example, or sorry, we use at most K edges in R, right? Where R is a subset of the E edges. And yeah, so looking at this example, we can try every possible path like this. That's like realistic, right? Because there would be no, like you wouldn't go back. That doesn't really make sense, right? So that's one path. And the path is like this path. And you look and see both of these paths, they take two restricted edges, and we want only at most once. So in this case, our output would be no, right? And thinking about this like intuitively, like how you would solve this question, you might think like, okay, what if we have like some sort of algorithm that will check every possible path between S and T, right? And then from there we can see like, okay, if any of those paths use less than or equal to K edges, then we're good. But the time complexity of that algorithm would like explode, and I think it's somewhere like of O of n factorial, right? Where n is the number of vertices. Oh, before you should pause this video and like make sure you understand the question. But yeah, so so it would be n factorial, and like the way I kind of think about it is like, okay, so given like the starting node, right? We can visit. It's kind of tricky, but you can say you can visit like that. Your next node that you can visit is like any of the n-1 nodes, and then from there it's like any of the n-2 nodes until finally you're at this one. That the time complexity might be wrong there, but like it's intuitive to see like that finding every possible path would like blow up your runtime, right? So we kind of have to think of a different way, right? And like the first thing you should always do after you understand the question, which you should have done already, is like make observations, right? And observation one is like, okay, it seems like there's never a case where you would want to prefer to like, or there's never a case where like it's bad to use a non-restricted edge, right? Because they don't accrue any cost at all. It's only restricted edges that accrue like some sort of cost, right? But like, and then you think like, okay, there's like a concept of like cost, right? There's restricted edges which seem to have like an infinite amount of cost compared to non-restricted edges. And then cost is like, you think about like, when you think of cost, you think of like weights, right? And then with that, you kind of think, okay, even though it says it's an unweighted, undirected graph, like the fact that there are some edges that are restricted and some edges that are not, like that's kind of like, in a sense, it being weighted, right? Where a restricted edge is like worth like infinitely more than a non-restricted edge, right? Like in comparison. Of course, this doesn't actually correspond to K, but it's like each one is corresponding to 1, if that makes sense. But I'm saying like relatively. Okay, so once we have that, we kind of like have like our like an idea, right? And we think like, okay, if there's like a way to find like some shortest path, right? Where the path, like in terms of shortest, in terms of like how we like greedily decide what shortest is like we prefer to like take a path with fewer restricted edges, right? Because a minimal path will take the least amount of restricted edges. Okay? So then we make like another observation. If I didn't say this already, but basically the shortest path is the path with least restricted edge usage. And if we can find that path with the least restricted edge usage and find out how many restricted edges that shortest path uses, if it's less than or equal to K, then we're good, right? Because we found that path. But if it's more than K, then we can return false, because if we already found that shortest path and it uses more than K edges, then no other path can use less than or equal to k edges, because that's how we defined it, right? So it looks like we have like some sort of idea now, and like now it's like, how do we actually like make it concrete, right? And like I said, right, if we can somehow assign like a non-restricted edge like some value, and then assign the restricted edge some other value, we can kind of like run some shortest path algorithm. And the one I'm thinking about is actually Dijkstra's, right? Because when you think of a shortest path algorithm with weights, you think of Dijkstra's, right? Okay. So how do we actually do this though? Can we conveniently, like, how would we like always prefer a restricted edge, or sorry, an unrestricted edge over a restricted edge, right? And then you think about like like some numbers, right? If we just make it infinity, right? Like this, that won't actually work in terms of running Dijkstra's, right? Because like then as soon as you encounter a restricted edge, you'll always like blow up to infinity. And then how would you like what would you even return? Or I mean, I guess you can backtrack and find out what path and then actually count the number of restricted edges. But what if we just like put this as 1, right? Because then once we're done, if say these are all 1, then the actual cost would be the number of restricted edges. But then what would be like the other ones? And I'll just tell you the answer. If you just put them as 0, this actually works perfectly. In this case, we always prefer to traverse the 0, or if we can, right? Because they always accrue like 0 additional cost. Okay. When I say prefer, like that's actually like not really how the algorithm works. That's more of like kind of like prims in a way, where it's like you prefer like you prefer like an edge that's like least expensive. But I'm talking about Dijkstra. So what I mean by prefer is like at every node that we're considering, like what is like the least amount of, or what is like the node that we're considering that has the least amount of cost to get there, right? Because that's how Dijkstra's works. So then that comes down to our algorithm. So what do we say, right? Our algorithm would make sense if we, let's actually define our algorithm, right? We're gonna assign every edge E, right, in R with weight 1. And then every edge, and then all other edges, so that means not in here, with weight 0. So that's kind of what we're doing here, right? Oops. Right? So once we do that, we can just run Dijkstra's algorithm. And then Dijkstra's algorithm returns like a cost, right? From S to T. And conveniently, that'll be the number of restricted edges, because we define 1 here and 1 here and 0 otherwise, right? So in that case, we run Dijkstra's algorithm and that returns to us a cost, right? And then if that cost is less than k, we can return true. Otherwise, we can return false. Okay, so now we want to prove like this algorithm is correct, right? So we can just say the algorithm returns true if and only if there exists an edge, or sorry, there exists like a path between S and T with K or less restricted edges. Okay? And I'm gonna give you intuition on like why you can just say this, right? You might think like, don't we have to prove like all cases, like, okay, if it's false, right? If we return false if there's like no path with K or less restricted edges, but I'm gonna say, well, actually, this actually already handles it for us. And the reason is the contrapositive, right? So you see this, right? This says true if path. Then that means by the contrapositive, not path, so implies not true, which is just false, right? And then it says path implies true. And then the contrapositive would be not true implies not path. So that's just all four of the cases, right? That's like conveniently shown here. So if we just prove both ways for this, we implicitly prove like for the false cases because not true is false, right? Okay, perfect. So first, what we want to do is if valid path exists, the algo returns true. Okay? So we're going to say there is a path. S to T using less than K restricted edges. That's just like definition of what it means for a valid path to exist, right? This implies that the path would have path has cost less than or equal to K, given the weights that we define. Right? And then we don't have to reprove like Dijkstra's algorithm, right? But we can just say that it outputs us what we need, right? Remember, things that we prove in class, like general algorithms, we never have to prove again. We can just say we run Dijkstra's with like, okay, this modification. In this case, we run Dijkstra's with like these weights on these edges. Dijkstra's algorithm finds path with smallest cost, right? It's the shortest path algorithm. That's how it works, and we proved that before. So, assuming that's not negative edges, and we did not define negative edges, right? It was only 0 and 1 with smallest cost. So, it will find that path or an even better path. Right? Like you'll either find like this path that's valid or even more, okay, I don't want to say more valid path because they're equally valid, but one that uses less restricted edges because that's how Dijkstra's works. So it returns true, right? Because that's how we define our algorithm here. Okay, now we gotta prove the other way. If algo returns true, valid path exists. Okay, so the algorithm found a path from S to T with cost less than or equal to K, right? Since weights match the number of restricted edges, this means that there's a path using less than or equal to K restricted edges. So a valid path exists. And we're just like deconstructing this, right? Because if the algorithm returns true, right? We look here, returns true. That means the algorithm found a path, or it found a path with the cost less than or equal to k, right? So let's just actually write that down. I don't know why I'm just saying that. Algo found path S to T with cost. That's what happens. That's the implication of it returning true, right? Okay. Weights or the cost matches number of restricted edges. Thus, this means there exists path, and we found it using less than or equal to k restricted edges. Okay, thus, valid path exists. So we proved both ways, right? Proved both ways. Okay, so that means we did our proof of correctness. Now what about time complexity? Well, assigning the weights edges, we're going to assign the weights each, we're going to assign each weight an edge, or sorry, we're going to assign each edge a weight, and that's going to be for each edge, right? Assigning weight. And we know from class that the time complexity of Dijkstra's algorithm is m plus n log n, right? Where n is the number of vertices and m is the number of edges. And of course, this last part right here. So this is like what we just showed. And this part is like the O of m. This is like the Dijkstra's one. Oh, sure, I'll just write it again. Okay, and then this is O of 1. Okay, so that means like this dominates this, so the final time complexity is this. Okay, so now we're done. And in this class, I think this is sufficient. But you might be wondering, is there like even a better way to do this? And there actually is. And actually, one of my friends, who's a competitive programmer, actually showed me how to do this more efficiently. But basically, if you notice, right, if we can somehow somehow compress this graph in a certain way, we can run BFS. So okay, what do I mean by that, right? Basically, like if there's a group of nodes that are connected, like with non-restricted edges, right? We can kind of like compress it. We can compress it. So let's say this is a restricted edge and this is a restricted edge. We can compress the graph and turn it into something like this. So in this case, this corresponds to this node. This corresponds to this node. This corresponds to this node. Notice how, like, it doesn't really matter. Like this is like the parent of this, right? It's kind of like union find. But okay, this is like getting a little complicated. But the main idea is like if you compress this graph like this, right? Then each one, like you basically make each connected component, where like the connected component we define it as like connected with only non-restricted edges, as we define it as just like a parent node, and define it like this. So make a new graph. We can just run a BFS from here to here, and notice how this time complexity will actually just be O of n plus m. But I think that's a little too complicated, so don't need to worry about that. But let's just kind of refresh what we did, right? So we analyzed the question, and we kind of like thought about it carefully, right? Basically, we saw like, okay, we need to somehow find a path, right? So already find a path. You can think of like all the different algorithms, like BFS, DFS, Dijkstra's. So those are like all the kind of like the path thingies, right? And we want to find a path that uses at most k edges, right? K edges. okay, so like there's a cost with and okay, we k edges like that kind of informs us like, okay, there's a cost to edges that are restricted and not a cost with edges that are not restricted, right? And we kind of see, okay, if we can find the shortest path, and the shortest path being a path that uses the least amount of restricted edges, then if that path uses less than or equal to k, then we're good. But if it uses more, then we know for a fact that there exists no other path with less, because we already find the shortest path, right? So, okay, we think about our shortest path algorithms. How many shortest path algorithms do we even have, right? I'm pretty sure we have like, what, like 3? There's Dijkstra's, there's Bellman-Ford. And then Bellman-Ford is just, what is it? Is that just like Dijkstra's, but for also, what was it called? Negative weights. And then we have like just regular BFS, right? But BFS is like for like non-weighted, right? But we have like some sort of weighting. So that just leaves Dijkstra, right? But how do we even use Dijkstra, right? How do we like define like the weights? Because we just said it was unweighted. Well, then that's where you have to be creative and be like, okay, what if we just define each edge that is restricted to have a weight of 1 and each edge that's not restricted to have a weight of 0? Then we can think about it intuitively, right? If we somehow find the shortest path with that, that means that we found the path with the least amount of restricted edges, okay? So that's how you think about it.